In the previous session, we were solving the problems on magnetization. Okay. So I think two problems we have solved. The third problem was that as the time was over, we couldn't solve it. So let us continue this problem and then I'll take the next concept. Question is, find the magnetization, that is capital M, in a magnetic material. In three different cases, you have to find M. So in each of these, unknown value is M only. You have to find M. We have to use different formulae, okay, according to the given data. So first case, mu is given, h is given. If mu is given, h is given, how to find m? We know that m is equals to chi into h, but chi is unknown to you. Okay, this is a direct relationship, but h is given to you. What is chi? Chi is, I think, mu r is equals to 1 plus chi. Okay, so how will you find chi from this? Mu r minus 1, because mu is given, not mu r is not given, I think mu is given to you. So again, in turn, to find chi, we require mu r. Mu r find करने के लिए we will make use of this equation, that is mu is equals to mu naught into mu r. So in turn, okay, via mu r find कीजिए इससे, mu by mu naught, mu is given 1.8 into 10 raised to minus 5, mu naught you know 4 pi into 10 raised to minus 7. So यहाँ से mu r आ जाएगा. Once mu r is known to you, you can find chi. Once chi is known to you, you can find m. So first we have calculated mu r. I have got, I'll not go on into the calculations part. Okay, mu by mu naught 14.32. So magnetization is, chi value I have directly taken like this, mu r minus 1. You can substitute separately mu r minus 1, which is equals to chi, and then substitute that here, chi. Okay, so I have found that m to be 1598.9. Magnetization, it is analogous to h. Okay, ampere per meter. Then second case, check. Data is mu r is given this time, and there are how many atoms? 8.3 into 10 raised to 28 atoms per meter cube. So these many atoms exist in an object. Assume एक magnetic material है, उसमें इतने atoms हैं, and each atom has a dipole moment. You know, we had taken this example, some volume we had considered. Each atom has got its own dipole moment. Okay, some assume there are 5 here. Okay, each will be having say m1, m2, m3. So, and all m1, m2, m3 all are same in this given question. So m dipole moment same hai sabka, 4.5 into 10 raised to minus 27. So यहाँ पर I have assumed 5 atoms, but how many atoms are there actually? 8.3 into 10 raised to 28. That is, if I assume there are n number of atoms in general, okay, yet n can be in this figure 5. In the given question, it is 8.3 into 10 raised to 28. If I have n different atoms and each atom has got m as the dipole moment, magnetization is given by m dipole moment, sum of, actually you take like this, sum of all those dipole moments per unit volume. Okay, so the sum of mi is what? Mi is same, m for all. So if m is same for n different atoms, it will become n times m by v. Okay, but what is given here? Number of atoms that are given per meter cube. So आपको ये दिए हैं, n by v is given to you. Okay, and the m value, each dipole moment is 4.5 into 10 raised to minus 27. So how can you calculate m? N times you have to make it m. The second question, magnetize. See, even though mu r is given, you have not used that anywhere. Okay, so n number of atoms are there, that is 8.3 into 10 raised to 28. M dipole moments are there, so n into m will give you the magnetization. Second one is just the multiplication. You may ask me where is volume, so it is per meter cube. Question is per meter cube, given data. Now third, we need to check magnetization you have to find given, okay, I have repeated this, B and see here, third one, B and chi value are given. So I have repeated that here. B and chi value are given to you. You need to find m. Main equation will be m equals to chi into h. Chi is directly given to you in the question. But what about h? Instead of h, flux density is given. So is there any relationship between B and H? Yes, we have. It is B equals to mu H. In Ampere's law and all, we have considered free space. But here we won't consider that. We will take it as generally mu. And what is mu? Mu is mu naught into mu R into H. So how can I find H here? H will be B by mu naught mu R. So I have calculated that here. Okay, directly I have substituted it in the formula. B is given to you in the question. Chi is also given to you in the question. But what is mu naught? 4.10 raised to minus 7. What is mu R? Mu R is again unknown. It is not given in the question. But chi is given. So from chi you can find mu R, because you know that mu R is equals to, here I have written, see, mu R is equals to 1 plus chi m. 15 plus 1, 16. So mu R is 16. B is already given in the question. Mu naught you know. And the chi m is also given to you. So magnetization you can find. M is analogous to H. H is equals to in amperes per meter. So in 3 different cases, you have calculated capital M. This is a question paper problem. Hope you got this. Formula याद रखो. Formula को situationally कौन सा data दिए हैं, क्या unknown है, उसके हिसाब से आपको use करना है. Now let us move to the next concept. It is the same repetition. Okay. Next concept, magnetic boundary conditions. See this term, boundary conditions. This is not the first time that we are looking here. We have already studied about some introduction part about boundary conditions somewhere previously also. Can anybody tell me where we have seen this boundary condition concept? Actually, we have seen what is the boundary condition while dealing with the uniqueness theorem. Okay, because at the boundary we consider some potential. Okay, I no need to recall what is uniqueness theorem, but I had given you some explanation about boundary condition and initial conditions. Okay, now when I talk about any magnetic material, okay, suppose आपके पास एक magnetic material है, you can consider this anything, copper or anything. Okay, assume that ये copper है. When some process is happening, some field gets created and this copper is being used somewhere in some practical application. Copper से कुछ आपने बनाया है, उसके अंदर एक fluid flow हो रहा है, assume करो. Okay, when the fluid flows, at the boundaries, how your whatever entity you are considering, how your entity, that is say fluid, it will behave at this boundaries. Okay, I am talking about the entity, the fluid. But when we talk about magnetic boundary conditions, our major concerns are fields. Okay, magnetic fields. So जब भी fields encounter होंगे at the boundaries, field का behavior कैसा होगा, that we have to analyze. At the boundaries, it plays a major role because I said heat transfer, fluid mechanics, right? In such cases, these play very important role. Your differential equations, your magnetic boundary conditions, initial conditions, how the things behave, okay, how the things change matters a lot. Okay. So what magnetic boundary conditions are? एक मटेरियल है आपके पास, मैग्नेटिक मटेरियल है, इस मटेरियल के बाउंड्री पे ये जो फील्ड है, either it can be flux density or magnetic field intensity, how these things will behave, okay, that we will analyze in this magnetic boundary conditions. Okay, and you know this B and H, they are vectors, and whenever just like imagine करो एक ray pass हो रहा है through a glass, light ray, it passes. So what will happen? You have already studied ray optics. I assume you have studied ray optics. So what will happen when this ray enters this interface? This is say air. This is your glass medium. So what will happen here? There is some bending, right? Some no doubt glass है. उसके बाद assume करो कि you have a water. When it enters water, this ray, you feel that the light ray, it appears to be a little bent. Okay, so all these changes happen, right? That is with respect to ray optics. I'm talking about optics there. Now when I talk about field terms at the boundaries, how this B and H will behave, okay, what changes occur, that we have to observe. uh, when we talk about these fields, we generally take, as B and H are vector quantities, any vector, okay, any vector, say A, it has two components. You know about this already. It has one horizontal component, say AH, one is vertical component, sorry, AB, right? So any vector has two components. Any vector can be resolved into two components, horizontal and vector. So in the similar manner, whenever such fields appear across the boundary of any magnetic material, okay, uh, in that B will also have two components. B vector hai, okay, it will have its horizontal component and vertical component. H will also have at the boundary horizontal component, vertical component. I have not named it, okay. Generally in vector analysis, vector calculus, you take H and V, right? H indicates horizontal, V indicates vertical component. Now when we talk about magnetism terms, this horizontal component, we call it tangential component. Tangent का मतलब क्या है? At some point, it just touches. That is nothing but horizontal itself, right? So horizontal is in analogous to tangential. So here in field, in magnetisms, in field theory, we talk about horizontal component as tangential component. So I will write here H tan or B tan. And talking about vertical, in vector analysis, we use V, small v, to indicate vertical component. In case of fields, we already know, generally we take either perpendicular word or normal. Normal indicates this vertical, right? Normal. That's why we take vertical component V instead of P, we use normal. N-O-R-M-A-L. Similarly, H also N-O-R-M-A-L. So at the boundary, okay, whenever this B or H, both we will see, B and H, they just cross the boundary of any magnetic material. How these horizontal component and vertical components will change, that we will study in this topic. Hope you understood the background. The magnetic boundary conditions, they explain the field discontinuity. That's what we will see, whether it is continuous or discontinuous. मैंने अभी आपको ray optics का example दिया था. Whenever a ray enters, right, it appears to be bent. This is the phenomenon, this change you observe in the optics part. But when we talk about magnetism, the change is in terms of either continuity or discontinuity. Something like एक surface है, यहाँ पे field जा रहा है, it can be P or H, whether it is continuous or is there any discontinuity happening when it touches the boundary. Okay, so we talk in terms of continuity or discontinuity. The study of these variations in the field, okay, we talk about both B and H. Okay, when the magnetic field, it travels from one medium to another medium. Obviously when I talk about some magnet, fields will be there somewhere else. Okay, conductor में जब current flow होता है, they will be circularly, they encircle this conductor. Similarly, when I talk about the field, when in terms of magnetizations and all, that particular object, it can be wood, it can be copper, it can be iron, it can be anything, it will acquire the properties of magnet. It means अंदर आपका field change हो रहा है, right? Internally I'm talking about. These fields, they will travel from one medium to another medium. That is very obvious. So that's why generally we say that the study of these variations from one medium to another medium, we will look into both B and H. Okay. So to study boundary conditions, two things are important for both B and H. Tangential component, which is nothing but horizontal component. Normal component, which is nothing but vertical component. So let us study each of these one by one. Now, this is the figure. You can see. Okay, this is the boundary. And यहाँ पर आपको दिख रहा है some shaded region is there. Just I have shaded this region to indicate ये आपका material है, magnetic material है, and ये अलग medium है. दोनों अलग-अलग mediums हैं. Okay, you can assume this to be air, or you can assume this to be one more conductor. Well, you can assume this to be one more magnetic material, but जिसका permittivity or permeability value अलग. Okay, you can assume जहां पर joints होते हैं, दो अलग-अलग चीजें जब हम join करते हैं, इसका characteristic अलग होता है, इसका characteristic अलग होता है. At the boundary, obviously the things will change. So ये light shade indicate करेगा कि this is one medium. This plain white indicates it is one more medium. See, mu1 is some medium permeability. mu2 is some other medium's permeability. Consider a boundary. This one, consider a boundary between two isotropic. You know what is isotropic, right? Structure wise, they are similar. Isotropic. Iso means same. Homogeneous. Homogeneous means the value is uniform. Either you take B or H, जो भी आप component calculate कर रहे हैं, at every point we will consider it to be homogeneous. And linear materials. Linear, just recall, we have studied classification of materials, linear and non-linear. Non-linear में we have considered diamagnetic and paramagnetic. In linear materials, ferromagnetic. Okay. So we have considered one linear material. You can consider iron. Okay. With different permeabilities, mu1 and mu2. Now, I'll highlight what is important for us now. At the boundary, you can see B, which is traveling from one medium to another medium, it will be resolved into two components. Similarly, H, it is also resolved into two components. Horizontally, tangential, TAN, for both B and H. Vertically is normal. I have written in short, NORM. Okay. Both B and H has two components, vector resolution. To understand the boundary conditions, we consider two different areas. One is the area and the concept that we use for Ampere's law. Ampere's law, जहाँ पे एक square loop consider करते हैं at the boundary. This randomly I have chosen. You can place it anywhere. Okay. This loop can be of any size. That's why generally we assume this is your delta W, and whatever this AD and BC are having, the length we take delta H. You can keep this rectangular path anywhere on the boundary. But what kind of diagram I have drawn? See here, this loop has half of its part inside one material, one medium. Half of its part is lying on in the another medium. That's in this way I have drawn. So consider this loop. So two different areas we will consider. One is Ampere's law के लिए एक loop imagine करेंगे, and to apply Gauss law, we will use a cylindrical contour. What we call contour means some surface. Okay, some cylindrical surface we will consider. इस cylinder के लिए you have top surface, bottom surface, and this perimeter will be there. Again, you can observe, assume करो कि इसका height delta H है, ये जो face है उसका area delta S है, top and bottom both. This cylinder is again kept in such a way that half of its part lies in one medium, half of its part lies in the second medium. Okay, this is how we analyze boundary condition. Possibility है कि ये दोनों regions के लिए how the fields will behave, continue होगा या discontinue होगा, we will try to understand. Hope you got the figure clarification. Now we will move to each component one by one. Now, to determine the boundary conditions, we will choose, as I said, एक closed path consider करेंगे so that we can apply Ampere's law there, and एक Gaussian surface imagine करेंगे जहाँ पे हम Gauss's law apply कर सकते हैं. Okay. Now, boundary conditions first हम horizontal component के लिए we will see. जो B का horizontal component है and H का जो horizontal component है, whether they will continue to travel from one medium to another medium or whether they'll have some discontinuity, we will see. Now, we know that from Ampere's law, we will consider for both Gaussian surface as well as a rectangular loop. Ampere's law says H dot dl, line integral, closed line integral equals to total current I. I have not mentioned the direction here, right? Wait, somewhere, yes, I have mentioned it here, clockwise direction. I have forgotten to give the direction. You can take any path. I think हमने class में ऐसे लिया है, anti-clockwise, right? You can choose any path because already as I have written the notes, let me continue with the same. But you can choose just थोड़े बहुत changes होंगे equations में. Okay, I'm considering in this direction. Now, from Ampere's law, we have considered one rectangular closed path A, B, C, D, A in a clockwise direction. So what will be the total line integral, which is equals to A to B? 4 different lines are there. For my ease, let me write it here. Where is A? Top. A, B, C, D, A, back. Okay, and यहाँ पे boundary है. I have taken here 1 and 2. Boundary पे just जहाँ touch हो रहा है, points are 1 and 2. So if I want, and the direction is clockwise direction. If I want to find the closed integral of this, I have to take 4 different line integrals, A to B, B to C, C to D, and D to A. Out of which, if I consider, I'm talking about H now, right? I'm talking about H now. For H, this is your horizontal component, H tan. Vertical now we will not consider. First, tangential we will see, horizontal. Out of these 4 lines, which 2 lines are parallel to this? We have to check. कौन से lines हैं out of this AB, BC, CD and DA? Which lines are parallel to this tangential component? Obviously, it is parallel, same line में है. AB and CD. What about this BC and AD? They are perpendicular to this tangential component. So what we are doing? We are considering the tangential components in this square loop. It's in this rectangular loop also. We are considering those lines which are having which are parallel to this tangential component because of the dot product. When we consider that BC and AD are vertical, so we are not considering its effect. When we talk about tangential component, in दोनों का effect हम नहीं लेंगे. We will consider only these 2 line integrals because they too are parallel to the tangent. Okay. The closed path is placed in, I have repeated this, in such a way that its 2 sides are parallel to the tangential component and the other 2 sides are perpendicular. As I told you, parallel जो है हम consider करेंगे, जो perpendicular है tangent को हम उसको निकाल देंगे, 0. We make it 0 to find the tangential component. This is one thing. Now, the closed path is such that half of its portion is in one medium and remaining half is in the other medium. You can observe here, यहाँ पे half part is in medium 1, half part is in medium 2. We have placed the loop in such way. Okay, with this what will happen? Suppose this is my original rectangular loop with some sides. Okay, now you can see this is one line. These two are parallel lines. As I try to shrink this, shrink means what? Kam karna. Okay. As I try to reduce this rectangular loop in such a way that this is first time. Okay, let me draw. Size wahi hai. You can see ye jo size this length hai. I am not changing that. वो same रहेगा. What is the change now? This is also delta W. Assume karo it has some length. This is same. बाउंड्री भी सेम है, जस्ट ये साइज रिड्यूस हो गया है. मींस ये जो आपका टोटल हाइट डेल्टा एच है, whose half part is in one medium, half part is in another medium, I am shrinking it. Delta H, I am shrinking it. कम करते, we are trying to reduce delta H. Next time, again, I will take delta W same. Further observe all the three figures. What is the change you observe? Height is getting reduced in all the three. So what we are doing? We are trying to shrink the height. Why it is required? That is the question. Because if you observe this figure, these AB and CD lines of this loop, they are far from the boundary. Boundary यहाँ पे है. ये जो line है, some distance पे है. ये line some distance पे है. What I am trying to do? This AB and CD lines, I am trying to bring them near to the boundary, क्योंकि मुझे boundary conditions पता करने हैं. So what will happen when I shrink my height to 0? That is, delta H tends to 0. AB and CD lines will become very, very, very close to 1 and 2 line, this line, and they will coincide. मतलब AB and CD line 1 2 पे overlap कर लेगा. Means now these 2 points indicate, this point indicates A also, 1 also, D also. This point B also, 2 also, and C also. So delta H, the way we start shrinking, AB line will come and sit on this 1 2 line. CD line will also come, slowly. When I reduce the delta, the height, it will come on line 1 2. So that's what it means. This closed path is small with the height delta H and width delta W. Width we are not changing. We are not touching the width. Observe. Okay, when we are changing the height, width is same line. क्योंकि हमको line 1 2 के ऊपर उसको touch कराना है. Hence, we are only interested in the value boundary 1 2. That's why what we do, we will try to reduce the height. Delta H tends to 0. If I do that, what will happen? ये जो size है reduce होते होते what will happen? It will come and sit on this line AB. AB, sorry, 1 2. 1 2 जो boundary का line है, AB will also come and overlap on this. CD will also come and overlap on this. So it is nothing but one single line integral, right? AB and CD, एक ही line, दो अलग अलग lines हैं, क्योंकि why I am telling two different lines? Even though they are coming and sitting on line 1 2 only, what is the direction we have assumed? See, एक line का direction इस पे ऐसे है, CD line's direction is in this way, opposite है. Okay, so I cannot say that the line integral is same. Directions अलग अलग है. That's why vertical we have not considered. We have made 0 0. So AB and CD जो हमको line integrals calculate करने हैं Ampere's law में. So what AB will be? AB will be H dot DL. H is your tangential component, because whatever you're talking about, this 1, 2, it is parallel to tangential component, somewhat parallel, okay, even though there is a curve here. Horizontal component or tangential component of H tan, ये दोनों parallel हैं. So I can replace H with H tan. I have taken 1. Okay, you can take AB or anything. You can take AB. I think that's better for AB. And what is the length of the line? Delta L. ये जो AB and CD के lengths हैं, delta W we have not changed. We have only touched the heights. Heights को हमने कम किया है. So length is delta W only. So DL will become delta W. This is for AB line. What about CD line? This is your loop. This is your point 1 and 2. A, B, C, D. For AB, we have taken H tan of AB. You can take dot delta W. अगर AB इस direction में है, तो CD इस direction में होगा. That's why I have taken minus. If you want to take this as minus, this will become plus. It's up to you. That's why अगर आपको anti-clockwise में directions लेने हैं, तो you just accordingly change the things. That's it. You can take any, you can assume any direction of the rectangular loop. So if one is positive, the second is negative. It can be of any. If you want this to be plus, this can be minus. If you want this to be negative, this will become plus. So according to the Ampere's law, AB plus CD, AB plus BC plus CD plus DA, इसमें से हमको सिर्फ ये जो horizontal हैं दो, because we are interested in tangential component, AB and CD हमने calculate किया है, इन दोनों को 0 किया है. So AB and CD are these things, H tan delta W minus H tan delta W. You can take this instead of tan 1, take AB. Here you can take CD. If you do this, substitute in the Ampere's law equation. Integration of line integral of H dot DL is equals to this value, that is H delta W, and a CD value minus H delta W. I'm substituting them equals to I. So take delta W common in this. What your equation will be? H tan 1 minus H tan 2 or tan AB tan CD is equals to current I by delta W. Okay. Now, what is I by delta W? Generally, you know that I by A is nothing but current divided by area will give you the current density. But यहाँ पर area ही नहीं है, because what we have done, ये जो rectangular loop है, इसका size हमने कम किया है, so that this has shrinked and AB line has come and it has sat on this 1, 2 boundary, and CD is also slowly moving and it has come on this boundary. So there is no question of area. यहाँ पे सिर्फ एक line बच गया है. That too length उसका क्या है? Value delta W we have assumed. So if this is delta W, there is no question of area, but there is a line of length. That's why I will say whatever I by delta W is there, it is surface current density. I won't use the term J because J के लिए हमको area चाहिए. But what I will use some other notation. But what is the change here? Denominator में आपको area नहीं है, because the size of the loop has shrink to one single line, which is coinciding with 1, 2. That's why I'm denoting this by some value K. So what will be your equation? H tan not delta W. I will cancel that. Don't consider this. Here itself, you can see H tan minus H tan 2 is equals to I by delta W, which is equals to K. That is H tan 1 minus H tan 2 is equals to K. Right? Now, looking at this equation, can you tell me when tangential components will become equal? आपके पास एक equation है A plus B equals to C. can or A minus B equals to C. Suppose this is your equation. When A and B are equal, when you will get A equals to B. It is very simple. Assume C equals to 0. अगर C 0 हो गया तो A will be equal to B. In that sense, when your H values of tan 1 and tan 2 are same. What is tan 1 and tan 2? H tan 1 is tangential component of AB line and H tan 2 is tangential component of CD line. AB line कौन से मीडियम में है? Originally, AB line is in medium 1 and CD line is in medium 2. So जब भी आपका H component एक मीडियम से दूसरे मीडियम को ट्रैवल करेगा, उसका जो tangential component है, ये 2 है, ये 1 है. Both now we have got, as per the equation analysis, we have got H tan 1 minus H tan 2 equals to K. That is, continuity nahi hai. There is some breakage. It is not moving. H tan 1 and tan 2 same होना है बोले तो value change नहीं हो रहा है अगर medium change होगा तो. Okay, without any, no, very smoothly it will flow. But it is not equals to 0. See here. H tan 1 minus H tan 2 is equals to K. It means they are not equal. ये equal होने के लिए condition क्या है? K should be equal to 0. तब ये दोनों equal हो सकते हैं. What is the meaning of K equals to 0? There is no surface current density. Okay. So H tan 1 minus H tan 2 will be 0 only when K is 0. Substituting H as B by mu. If I do that, because I want for both B and H, right? That's why I have substituted instead of H, B tan 1